Good afternoon, everybody. We are back. This is the end of the hackathon, nearly so. We still have a few steps to take, but it was really great. So we have all of the teams that are connected. We have the people in the evaluation board, they logged in. We are all a bit tired, but I think we're all very, very excited. So the organization of the session today is such that now I will give a few introductory remarks. I will show you a new video that we have produced, and then we leave the floor to the different teams. Each of them will have, say, maximum 15 minutes for showing what they developed and the fundamentals of what they did. And then there will be an interaction with the board, which is going to last a few minutes. But since you are not time constrained, we take the time it takes to have the best possible understanding of what you did. And I want to thank you all. And now, if I can share the screen, then I want to show you the video that we actually realized. Let me say if I can. Here we go. Available on a boot smoother than tomorrow is going to benefit for the home, your washing machine, and the mobile phone. Okay, I don't know whether
the sound wasn't there.
The sound, you couldn't hear the sound.
No.
When I share the video, I don't share the voice as well. Let me try. Okay. Yes. Let me see here. Share computer sound as well. Okay. I can click both. I can in principle click both. Let me see. Let's see. Now I go back. And here we go. Let's try. 100 years ago, the discovery of the quantum properties of nature triggered a revolution in science. Now, quantum technologies are entering our everyday life. Random power harnesses the quantum properties of semiconductors to generate virtually endless strings of random bits in a dedicated silicon structure. Irreducible unpredictability of the quantum world makes the strings secure to protect our digital life through unbreakable cryptographic keys and protocols. Today, the platform is available on a board smaller than a credit card. Tomorrow, it is going to be in a chip for your home, your washing machine, and your mobile phone. That's it. I hope you could hear the music and the wording as well.
Yes, yes. Now it was fine.
Good. This is making me happy. It was really not easy to get to this point in 72 hours, but I think assisted by the people that are babysitting the university in the production for short videos, we did reasonably well. It's a little bit, say, Blade Runner style, but it's not bad. Okay, now we go back to the hackathon, and so we're ready to go. And I would say team number 1. Are you ready? To get to this point in 72 hours, but I think assisted by the people that are taking the university in the production.
Hello, can you hear us?
Hello? Yes, yes, I can. Yes, we can.
Hi.
Okay. Now we.
Why are we first? Because the name.
Hello.
Hello.
Nice to see you.
Yes, it has been a great 3 days. So should we start the presentation immediately?
Yes, please. Share your screen, and then we kindly ask you after the presentation also to send us the PDF file.
Yes.
Sure. Okay. Can you guys see?
Yes.
Okay, so you're starting, right?
Yes, okay. So we are a Hexagon team from Middle East Technical University and from IRME Group, that stands for the Research and Application Center for Space and Accelerator Technologies. We are 3 members. Sorry, it doesn't work. So this is Rahim. He is our computer engineer. Then we have Arda, who is our physicist, and I am from the micro and nanotechnology department. We work with simulations a lot.
Why isn't it?
So yes, sorry for the problem. We work with simulations a lot, so we decided that we were going to focus on GN4. And we needed advisors, of course, for this problem, because GN4 is very complicated. So our advisor, our professor, who has helped us a lot, Professor Bilge Demirkos, and we also had another student who was originally going to join us, Abdurrahman Al-Baraudi, who tried to help us, although he got sick, as we mentioned. Through our work, we had an initial proposal in the beginning. We decided that we wanted to calculate particle showers in high energy collisions, in high energy physics, who are rare events. A very simple, straight to the point explanation, I would say, is this scattering progression diagram, who shows 2 particles, 2 primary particles colliding with each other, and firstly creating some, let's say some, oh my God, sorry. Just go back. Okay, sorry. So as you can see, the pink ones create the first 4 particles that are scattered, and then it continues to the green and blue ones. Basically, they are secondaries and tertiary particles that are created, each of which
our video is turned off, right?
Oh, okay. Each of which requires different paths and requires different energies cross sections. So the physics evolves from 2-body problem, two particles scattering with each other, to maybe an infinite amount of particles reacting in the same, let's say, tree branch. So the diagrams are actually very complicated, and the physics behind it is complicated. What was very important about it is the resonance areas. So resonance regions, as we can see in this graph, in the, let's say, the very scattered area of the graph, the resonance regions is where the particles have their probabilities of interaction. So, for example, we have cross-section resonance regions. We have in this resonance region in here, the possibility of inelastic proton electron scatterings. So when we go from the right to left, we see that the changes are very abrupt, and some of these changes don't get picked up by the current pseudo-random generators. They get averaged out. So we do not get really truly random data, which means low probability QCDs will get ignored. What we try to do in our project is to use GN4 and true strings of numbers and bins to create the highest, like to give equal probability to all the possible scatterings and all the possible QCD reactions. The physics in this case was not our main problem, because implementing the GN4 code was more, let's say, time consuming. So we want to focus on the code and the implementation of the generator, or the random bits that we got from the random power data pool, which was thankfully quite big for our case. And we wanted to put that in GN4. So our friend, the computer engineer, will explain the implementation.
All right. Hello, everyone. So as my friend sort of explained, well, briefly sort of glossed over some of the more theoretical components, I will talk about more of the practical stuff and what we sort of actually did. So first things first is GN4 is a pretty big, high energy physics simulation software. And so the first task was to debug it and try to figure out how it actually generates random numbers. So the first step was basically, so we all use GN4 every now and then, but we never really dug into the source files to try to sort of understand how it all connects. So that took a couple hours to sort of figure out. Afterwards, we figured out how the output of a random number generator is. And what we did then is we used Python to first pull the data that you guys graciously provided, and we converted it into the format necessary for GN4, which is essentially a range of 0 to 1, and in doubles, which is about 15 digits integer at max. And in primarily two basic forms, the form of flat and flat array. Flat being a single random value between 0 and 1, and flat array being an array of the previously mentioned values. Then, because most of GN4 is basically compiled upon C++, we wrote a C++ program to simulate a pseudo-random number generator, except instead of generating a random number, it acts like a generator and outputs the real number that we feed it from the bin file. So one of the more complicated things was that, as some of you, those who've used GN4 might know, and those of you who haven't used it, I'm explaining now, there are basically 8 core generators, or 8 different algorithms that GN4 uses to come up with random numbers. And then on top of that, there's about 20 to 25 different inherited classes, which make use of those generators and for different various purposes. So debugging this was kind of like going through a maze. So as you can see here, this is just an example of a ton of the files that we sort of had to go through to figure out which generator and how exactly it's performing. And once we were able to do that, the job was to basically hack GN4. So from the 8 core generators, as I mentioned previously, there were 25 others. And a large chunk of our time was spent designing a generator that could efficiently fit within GN4. And finally, to integrate it so that when we compile GN4, it uses our generator as well. And in the end, we sort of validated GN4's pseudo-random number generation in a sort of hacky way, which I'll get to in a bit. So first off, we successfully got our own function to feed numbers into the generator. So we had a verbose setting where we set out every time our generator was called, and it would tell us, and it would also give us the number that was being used as a random number. So this is what we use to sort of make sure that the values that Geant4 is getting is the values that it should be getting from any other pseudo-random number generator. And the results were that we successfully did implement a true random number pseudo generator, in this case, the generator being the pseudo part. And we were able to create high energy physics simulation with these true random numbers. And one key element is that they are kind of reproducible. So generally, the benefit that we get is that we get, as my friends explained theoretically, we get true random numbers, which help us plot the high energy physics interactions better. But in the event that we need to share this, initially we coded a way to use the bit streams that you guys sent in the form of bin file. So then reverse engineering that, we realized that whatever true random number we use, we can actually store it and save it and then compress it. So that if, for example, someone wants to reproduce our simulations, instead of giving them a seed, we'd be giving them a random number file, which would basically contain the list of numbers they could use to simulate. Right, so when we ran it, of course, we get a bunch of physics results. The first thing we did was we plotted a histogram that one of our MS students is working on for his thesis. It basically, sorry, I'm missing a slide. Well, okay, so basically it's a histogram of protons at about a 380 kilometer range. And so what we see here right now is, yeah, sorry, not the output. This is sort of the input of the bins where we select how we want to feed data into it. And the results that we get, it might look a little confusing, so let me break it down. On the left is the data that we would normally get using a pseudo-random number generator. And on the right is the data that we get. Looks like the presentation sort of mixed up a little. Okay, so you can see the boxes. So the first major problem we had was that, unfortunately, so we have access to a kind of a server computer that usually does all of our simulations for us. But unfortunately, it had some problems and we weren't able to use it for a week now. So we were kind of stuck on using our laptops, which aren't very good at simulations. So at max, after we implemented it, we were only able to get about 28,000 particles, whereas normally we can get up to 1 billion particles. So the error bars are pretty high. But a key thing to note is that, let me turn on the laser pointer, right, is that generally, if you look at the overall shape, we are starting to get a similar shape. So we have a plot that goes slightly up, then down, then up over here. And we do get something like that here, just that because our statistics is so low, our error bars are quite high. And one of the things that we actually plan to do is we plan to leave it running with our server in the future with a source of TRNG so that we can actually get better data and understand if we're able to properly validate the physics results or not. As a bonus, one other thing that we found out, which we didn't know, perhaps some of you might have, but what we didn't know was that when Geant4 is checking for overlapping between geometrical shapes, it actually uses RNGs as well to make sure that a particular value isn't hitting two different spaces at once. We didn't know that it uses RNGs. And when we were plotting some stuff, we noticed that our verbose setting was still turned on, and over here at the bottom, we're actually, it's actually using our random number generator. So this was kind of a surprise that it actually uses RNGs for this purpose. So yeah. For the future, we actually plan to continue this, and we hope to be able to make longer simulations so we can collect more data and actually have a proper comparison with the pseudo-random number physics data. And if any of you are interested, feel free to contact us. We can share the information with you. And we also hope to improve the speed of our implementation. Granted, we aren't exactly experts at C++. We mostly work with Python and other similar languages. So C++ was kind of, I mean, we knew it, but it was still, we weren't really good at it. So our implementation, at least I personally think, could have been better and faster, and allowing us to get more particles per second than what we got right now. We think that in the future, we might be able to further validate Geant4 pseudo-random number generators, and this could possibly, I mean, I'm not sure right now, but it could possibly turn into a paper, in which case, we'd love to sort of contact you guys again in the future, and maybe we could, you know, talk about this further if possible. So in the end, we'd like to give special thanks to the laboratory that usually provides us the servers and the office space and gave us a ton of help. the Evemer Lab, which of course is run by our advisor, Professor Bilge Demirkos. And we'd like to thank the Random Power Project for answering a ton of our questions. I personally wasn't too active in the question answer sessions, but I was overhearing everything. So we're all quite grateful and thankful.
Thank you.
And of course, special thanks to our advisors who often guided us on what to do and what not to do during this project. So yeah, thank you very much. Sorry for the slight delay in our presentation. We were still collecting data up until the last minute to try to get as much as we can. And that's why it's 2,600 something and not a proper full number. So we really apologize for that.
For our random files, we got up to 100 million particles and random numbers to try to simulate as much as we could. But obviously that means that we need a lot more time.
So we apologize for that. And like I said, if anyone is interested in following up, please feel free to contact us. We can share whatever we've learned. And thank you. Does anyone have any questions?
Thank you very much. So very well done, very clear. I believe most of the question will be on the physics side. So I'm afraid it will be me asking. But before I open the floor to questions, let me tell you that, of course, we will be happy to continue with you. So if you need the board, if you need more data, if you need more randomness, just let us know and we keep in touch for sure. Now,
thank you so much.
Thank you.
Before I ask my own questions by being a particle physicist, is there anybody in the audience or in the board that is curious about what I said? Okay, so I just get started. So the first one is really trivial. What is unclear to me is, for instance, to have an indication about the amount of randomness that you need. Do you know actually how many random numbers you need per event?
So from what we noticed, every time that we run the simulations, every, let's say, millisecond, there is a new number generated, which we think that it takes a random number every time it creates an event. From our statistics, we saw that it implemented about 1 million random data that implemented into the simulations. But because we had to run multiple parallel simulations, we are not sure. In which case we decided to, because in this case, we decided to really increase the number of random numbers that we could provide to the system, just in case it exceeded.
Yes, but in principle, you can measure it, no? Because, I mean, since you're providing your own routine for the RNG, if you have, say, a pointer, which is telling where in the list you're entering after every event, you can have an indication of the amount of data that are required per event, which is important to properly size actually the flux that you need. So in principle, in principle, to me, I mean, to my simple mind, it shouldn't be much of an issue, and it should give you really, without entering the details, the data set which is required.
Well, in terms of coding it, we actually set it for about 1 random number for every histogram bin and 1 random number for each interaction. But we might look into changing that further to see if we can get better results. We also contacted someone who at CERN who does these validations, and he actually hosts a website for Geant4 validations. Understandably, he probably didn't get back to us within the 2 days that we were working, but he's in charge of most of the validations, and we were also hoping to get in touch with him to see his thoughts on this matter. So, I mean, obviously, we're not experts as well in this area, since we're also learning as we go along. So it'll be helpful if we could get someone who's really an expert in validating Geant4 results and figuring out what he recommends to do. Okay. And of course, we can let you know as well if you're interested.
Yes. Then the other question that I had was related to the fact that to the use of the random numbers, because you said that your primary input is turning the bits into digits between 0 and 1, which is obvious. And let me tell you, and you said that, if I'm not mistaken, that you did it using 15 bits length, right?
Yes. 15 integers, but in general, for the computer, we simply kept it as doubles.
Okay, but how do you make the normalization? This is something that, because you have to make sure that you have an equal spacing between the numbers.
Okay, so what we did, we took a more numerical approach rather than a theoretical approach. So the first thing that we did was when we took your, when we downloaded the data stream that you gave us, the first thing that we did was we converted it into normal integers and we sort of plotted a histogram, and we wanted to see the distribution of it. And naturally, the histogram came out to be quite flat. In fact, initially, we were getting some overflows. So the ends were a lot larger than the middle, and we thought this doesn't make sense. And we realized, okay, that's sort of a bug in our code. So what we did for normalization is we, every single bit that we got was random and independent from the other bit. So what we did was we took 6 bits, which is what one of the generators in Geant4 uses as in output. Sorry, not 6 bits, I apologize, 6 bytes. So every 6 bytes, we took that data, turned it into an integer, and we used that as a random number. And to normalize it, we divided it by the largest possible value of 6 bytes, which, for example, then which would be 1111111.
Yes.
And
Yes,
by
yes.
right, and then dividing it. So since that's the largest,
So you do it by normalizing to the largest integers that you can
yes.
generate. Yeah. There's, you know, that there's a story in literature about the fact that if you do so, you have to be a little bit careful, because it's not excluded that actually you're not parceling the discrete state in an even segment. But okay, it's a detail.
Let me take a note of that. Could you, sorry, repeat that? Because that's something I should probably keep in
Yeah.
mind.
It's if you look actually in literature, I don't have actually a paper here with me in my desk. You have to make sure about the way you go for the normalization between 0 to 1. So, and not necessarily dividing by the largest integer is actually providing you really a uniformly distributed distribution. Because of course it might be uniform, but not, say, equal density.
Right. One of the issues.
It's a numerical problem where people were investing some time.
Something quite similar, which could be interesting for the others as well, was that when we were doing our own research, one problem with true random number generators was that sometimes true randomness is actually something that's not preferable. For example, before Apple Music, music companies that would use shuffle, you know, for iPods and stuff, they would use true random, try to simulate true random, but then the same song would come up again and again every now and then, and people didn't like that. So they had to tweak their random pseudo-random generator and make it biased towards unseen numbers, just so people could think that it's random, you know? So it kind of reminds me of that, and you're right, we should keep it in mind. Thank you very much.
Okay, thank you very much. I also got some food. Fantastic. I can survive.
So I would have some questions following exactly what we already discussed, and it's an interesting point. So whether or not you need true random numbers for this application. So what is exactly your plan to really try and test how much true randomness you need versus pseudo random? And another question related to that is there any gain? Because obviously true random numbers don't necessarily get to the throughput you might need for generating large quantities of events in particle physics, as to whether you investigated whether it makes sense to maybe randomize the seed with a true source and then have a limited amount of events which are of randomness generated by a pseudo random way, which allows you to get very large amount of numbers quickly. And then you would change the seed. I mean, I'm not saying I have a path forward, but I'm just trying to think, what's your trade-off between like generated billions of events that are needed for LHC and possibly other longer term, applications versus the availability of randomness. Hopefully, of course, in a couple of years, we'll have infinite, quickly accessible random numbers at the tip of our hands, right?
Right. So to address your questions, well, the first thing that I should clarify, which I perhaps missed in the presentation, was that while physics evaluation is our goal, right now we only had time to sort of check out the primary energy production of the histograms. And unfortunately, as I mentioned before, we're not exactly experts at validation. When this hackathon came up, the first thought, one of our students, Abdurrahman, who's sick now, who became an advisor, he and another of our friends was working on Geant4, and we had some experience with Geant4 as well. This thought came into our mind, why don't we try to validate it like this? So it was actually a week ago that we decided, okay, this is a good idea, and we should try to look into it. So then we started to begin our research, and initially we thought the first thing we should do is try to feed our true random number generator into our into Geant4. The scope of our project for this particular hackathon was try to get our foot in the door with this project to sort of find a way where we could feed true random numbers by building a generator that mimics the other generators that Geant4 already uses, and to try to sort of, once we get our foot in the door, once we can feed random numbers into it, then we thought, okay, if we have time, or perhaps in the future, since this idea we seem to like it a lot, we'll look into methods on how we can better account for biases in true random numbers as well as precisely how many random numbers we should use, and if we can sort of, mix match. One of the ideas we had actually was to use random numbers to generate seeds randomly, and then sort of use those seeds to, I believe you mentioned this in one of your points as well, and then, and then using the seeds to, sort of quicken and hasten the production. We thought about that, and we actually thought that this is something you could try later. One of the reasons we didn't do this, and perhaps you might be more understanding of this, more than us at least, was that our thought was that even if we use the true random numbers to generate seeds randomly, at the end of the day, they're still seeds. So the process they go through to create a pseudo-random number wouldn't change much. So we were sort of thinking, would it really affect in the long term if we randomly decided the seed? Most seed generations these days already use something, for example, the heat generated by a laptop or some electrical currents. So would our true random be any different than that? That's something we thought, okay, we can sort of think about this in the future as it comes along. And lastly, for any question that we didn't have, we did get in touch. We did try to get in touch with the person who's an expert. So hopefully he'll also be able to answer some questions that we have. So I apologize.
Right. No worries. Thank you very much. I just wanted to see where you were thinking. I think anyhow we will literally collaborate on this. I mean, there will be lots of people interested. It's a topic that interests me. I know at CERN people at Open Lab are interested. Obviously, with Bilge there, you have a good team that will follow this up. So we'll be in touch in any case. I just wanted to get a bit your perspective on this. But thank you very much, and we'll anyhow be in touch.
Okay, thank you so much.
Thank you. Well done. So do we have any other question? If we don't, then I thank you again, and we move to team number 2.
Thank you very much.
You.
Ashish? I'm afraid I can't hear your voice.
Hello, can you hear?
Yes. Hello, Siddharth. Now I can.
Hi. 1 minute, I'm just. Can you see the slides?
Yes.
So, hi everyone. This is Siddharth Sankarswamy, and my teammate is Ashish Mittal. So I work as a researcher in Barcelona Supercomputing Center, and Ashish works as software engineer in Infosys. So we are going to present today this work on use of homomorphic encryption with quantum random number generators, mostly for financial transactions and payment application. So this is our individual project. So no company or universities is involved with it. So it's in our individual level. So the basic flow of a payment processing app is like a user submits his card number, maybe debit card or credit card numbers at the POS or the merchant payment site, and it goes to the merchant bank. It validates something, and again it goes to the credit card association to find out which type of card it is, and after that it goes to the issuer bank where the whole validation takes place and the payment is approved. So at each point of the transaction, there are a lot of vulnerabilities at the merchant's bank side, at the credit card association, and at the issuer bank, where the data may be intercepted and the credentials of the user may be hacked. So there is a need to secure that, because at each of the site, the encrypted data, though it is encrypted when you just submit your credentials, it has to be decrypted fast in order to process the data, in order to validate or in order to find out which type of card it is, and in order to authorize. So it cannot, present system doesn't allow processing on the encrypted data, so it has to be decrypted first, processed, and again re-encrypted. So in that small span of time, there is a chance that some eavesdropper may hack or intercept the sensitive information of the users. So mostly we can go through the payment application architecture, which consists of interfaces, which is basically web application or Android app, where the user interacts or submits its credentials, and the modules, which are responsible for driving the payment transactions flow. So interfaces are basically POI device interface or POS API or payment processing link, and modules are basically router, store and forward, and batch processing, timeout reversal. So these are basically the transaction flow types. And there are certain areas of vulnerabilities when the data is stored in the memory. So some data are also stored in the merchant side for further analysis of the statistics when the data is in transit, and when the application code uses it. So there are many points of vulnerability. So you can see in the diagrams. So this is the merchant store, which is the merchant side, maybe where the payment application is there, and there is data at different points. Sometimes data is in transit, sometimes is in, stored in the memory, and sometimes it's in transit to another point, that is the merchant bank, or it may be in transit to the card association or the issuer bank. So these are the points of vulnerabilities where there is a probability of attack and hacking of sensitive information. So some PCI network protection requirements, where the encryption is required, and where it is mandatory to find out the encryption is there. So these are some data which I got from the PCI network requirement protocols. So between the POS and payment gateway, you need encryption, and POS and storage, you need encryption. Uh, in the LAN side, the POS and store server, you do not need. So there are some relaxation at some of the points which are exploited now in different ways by the hacker. So our proposed system deals with computing on encrypted data. Like it's a blindfolded computation. Homomorphic encryption is basically a blindfolded computation on encrypted data without the need of decrypting it, computing it on the encrypted data and getting the encrypted result, so as to when we decrypt at the client side, we get the original result which we want. So basically, the uh, points where we saw that the vulnerabilities can exist, those points should not be able to access the data, and the data should be processed in the encrypted manner. So that is the aim, and QRNG makes it more secure. So use of QRNG at different points in the homomorphic encryption algorithm, as we'll see in the later slides, makes it more secure. So nowhere in the network the data is ever decrypted, and it meets the security goal of confidentiality and integrity. Uh, Security of data depends on the encryption scheme, because if your encryption scheme is the strongest one, then nothing can go wrong, because it's in the encrypted form, and the processing is done on the encrypted data only. So here the encryption scheme is based on the lattice-based encryption, which is a post-quantum cryptography encryption scheme, and quite secure, one of the most secure encryption scheme. So that also is nice for the security purpose of such applications. And it also reduces the probability of side channel attacks, because some side channel attacks are involved with the storage units. When the data is stored in a memory, it is not in the encrypted form, or when the data is processed in the RAM, it is not in the encrypted form. So at that time, some hackers can do the side channel attacks, like finding out analysis of the power consumed, or analysis of some sounds, acoustic cryptanalysis, what we call, from some of the components of the processor. So that takes place if that the probability of such side channel attacks are more if there are more number of encryption and decryption at different points in the transactions. So as this type of homomorphic encryption reduces the number of encryption decryption, as the data is processed in an encrypted form, so the probability of side channel attacks are reduced. There are different points which we found in the homomorphic encryption algorithm where the quantum random numbers can be used. Basically, they are using the pseudo random numbers from the classical random number generators now. So there are this homomorphic encryption library which we have used for this hackathon. It is called HELib. We'll see that later, and that uses some number theoretic library called NTL, and that NTL uses some random big integer number. So uh, at that point, we can use such random numbers generated from this QRNG. And there are certain points during the encryption where the key generation required random scalar and error vector to be generated, where these random numbers can be helpful. And for random noise generation, so in this lattice-based encryption, basically we have some error or noise being added in the encryption intentionally because it gives rise to a hard problem on lattices, which is as hard to solve, even more harder to solve than the factorization problem also. So that is the learning with error problems. So because of that, some noise need to be added. So random numbers can help in the random noise generations, and random numbers can help in the bootstrapping process. So bootstrapping is a process where we do recryption, that is re-encryption, encrypting the text several times in order to control the error propagation when it is being processed as a circuit. So in that situation, we need some random numbers to be used frequently. So this in that stage also random numbers can be helpful. So if we have a QRNG to generate somewhat true random numbers, then it can be helpful in security at this points. And we have also used modified the homomorphic library in this hackathon to use random numbers generated from the QRNG, which is being provided to us, and we have implemented it in the algorithm also. So another advantage of in silico QRNG, which it promises to be, is that it will be there with very local to the processing, the encryption process. We don't have to request it to the over the network and again get back the response. So in silico QRNG is quite helpful because it will reduce the network vulnerabilities and the network delays where we are requesting some random numbers and it is coming, and again we are using that in our algorithms to process it. So it is a good way of using a pocket random number, in silico random number, which is local to our processing machine. And also we are using some this is a small modification, some random extractor, because we get a bits in bulk, and at different points where I have mentioned here, the random numbers are used to as different bits. In some of the cases it is 256 bit random number, in some of the case 1024, in some of the case there is different bit length of random numbers which is used at different points in homomorphic encryption. So we extract it using a random extractor and use it accordingly. So libraries used is HLF, which is an open source library, which is based on the BGV fully homomorphic encryption scheme, and it is a C++ library, and it takes the help of two other libraries as mentioned. One is NTL library, which is the number theory library, and GMP library, that is all that helps the NTL library for floating point operations and multi-precision operations. So it helps in different types of integer operations and operations over various rings, fields, and groups which are used in the homomorphic encryption. So, so these are the two libraries, NTL and GMP libraries, which are being used with the HELib. So we need to install that before using HLib. We also had some optimizations to this, because as you know, homomorphic encryption is not quite practical and it takes a lot of time. So this project I tried during my masters, and I'm still continuing it now, putting different optimizations wherever possible. So in this hackathon, I tried to parallelize the homomorphic encryption using OpenMPI library, and there is another optimization which we did. So basically in the bootstrapping operation, there are arithmetic circuits which are there, and there are different levels to the circuit. So as and when the level of circuit increases, it takes more time to process or encrypt or re-encrypt the data. So the main thing is how we can reduce the level or depth of the circuit. So circuit reduction is one of the important problem there. And we have used a result from the paper by Neeraj Kayal. He's a theoretical computer scientist, and there have been subsequent papers from him on circuit reduction from arbitrary depth to depth 3 circuits. So basically, we are reducing it to depth 3. There will be 3 levels, and because of which the circuit is highly parallelizable. So parallelly, there will be a number of operations, and we have used OpenMPI to have certain level of parallelism. We could not have all level of parallelism because it's very hard to do in 2 days. There are a lot of errors in that, so we had certain level of parallelism in that, which is a result from the circuit reduction algorithm. So this is one of the optimization. Another thing is using the module LWE. So this LWE is one of the basic of learning with error methods used. First is ring, second is standard, and third is module LWE. Ring LWE is quite efficient. In terms of the time taken for operation is quite less, but it's less secure than standard LWE. Standard LWE is more secure but less efficient. But in the middle, what comes is module LWE. So if we use such type of structures, which can be generated from the NTL and GMP library, so it can combine best of both the worlds. Like we can have a trade-off between safety and efficiency of the algorithms. So that one also is used. So these are some results which we got for different bits of encryptions and different levels of operation. So this is plain HLIP. We didn't do any modification, and these were the result we got in addition and multiplication operations. So basically, what happens in the card processing or payment processing thing, the credentials are hashed and they're matched with some of the details in the database to find out if there is a match successful or not. So basically, this homomorphic encryption relies on addition, multiplication, and subtraction, these three operations to construct all types of operations. So analyzing the timing of these operations can be helpful. So that's why we analyze the time here. Mostly multiplication takes more time. So these are some graphs like with the number of message bits, what is the time taken in millisecond for multiplication, and this is for the addition operations, what is the time taken, and this is some comparison. The addition is not that visible because it's I think the scaling need to be done properly. We couldn't do that, but yes, addition is just quite similar to the x-axis. So, and this is the modified HLIP, the optimizations we discussed. So applying some of those optimizations, we have obtained certain reductions in the time, and these are certain reductions of adding to ciphertext. So Gentry's scheme is basically the BGB scheme, which is originally in the HLIP library. So that is means not much reductions, but yes, somewhat we could get some reductions in that. And this is for adding a constant to the ciphertext. This is the multiplied to ciphertexts. So there, this is the bit rates. I have sent some bit rates to Massimo, but these are some modified bit rates with a small number of modifications. Like we got some 0.0001 MB per second extra encryption in first 3 cases, and 0.0001 MB per second for last case. So very small time modification, but yes, whatever we could do in these 2 days. So that is. So our future work is to more look into optimizations of homomorphic encryption, because it is a continuing work, continuing research in academia now, because people are continuously looking at how to reduce the time of the encryption and how to use it more efficiently. And also, we have some NIST results on the QRNG also, but we'll share it. We have created a document of it, so that to secure the algorithm better and better. So that
Okay.
is also cool. These are the
Thank you. Which is very interesting. What you did, yeah, I can see reference 4 is the reference that everybody knows. Also reference 3 are the one that everybody knows whenever you get started, you want to get started with the full homomorphic encryption. So yes, the use case is somehow very clear, but you are, if I'm not mistaken, to the very early stage of optimizing the basic tool that you will be using for your final use case. So the use case is absolutely relevant, but the question is, if you, for instance, take a snapshot of where you are by now, these performances would be enough to process the volume of data that are expected in your use case, your end user application, or how far you are.
So this was the question. When I first started this project, we were means at very low time. Means the time which I am showing now, it is much more efficient now. But before it was very less, very more I should say, the time taken for processing. And if you say about the volume of data and going by the statistics for number of credit card or card being processed per month or per day, so this figure is very less. We have to work more on this, and the time is not as required. I am still continuing to explore other types of homomorphic scheme. Like I'm also exploring the seal homomorphic encryption by Microsoft, and there are other different types of encryption scheme.
Yeah,
IBM
this
has
is
one.
the other question that I had. So if you compare the performance that you have to seal, for instance, where are you?
No, it's not that great as seal, but it's quite flexible. Like if you compare, I can give you the example of two programming languages. Like there is Python and there is C++. I can use HELib more efficiently and in a better way as I like. I can go inside that and I can modify the library. I can change some mathematical libraries or improve upon that. So it's quite open source in terms, and quite flexible to modify and change. So I think if I continue work on this, I will be exploring Seal and other libraries in the
Yeah.
process.
And the other
But
question that I have, I don't know whether you are aware of what is called the full homomorphic encryption over the torus, which is another scheme.
yeah, I have heard that, but I am not aware of that. Maybe it is something related to the geometry of torus, because
Yes, it was
because
proposed by a French mathematician, and actually, I
yeah.
think, if I'm not mistaken, is also currently used at Infer, the company that gave the speech yesterday. And it was claimed to be the fastest
I think
homomorphic encryption scheme that was ever built, at least so far.
yes,
So
I
I'm
have still to
just
read
curious
that.
to
I
know
have not
whether you
read that.
were aware. But okay, so let's say you are improving the essence, so the basic of your application, but you haven't gone so far really to estimate or to set it up for your application. You
No,
really
no, no,
okay.
no. We
And
are
then,
just in the
but
process of
what was,
improving that.
but it's clear actually the role that the QRNG has, and one of the reasons why we are also interested in the homomorphic encryption is because, as you said yourself, random numbers are required not only for the key generation, but in every step you take in homomorphic encryption. So you need high quality, large volume from the encryption itself to the noise that you had to the keys. But now it's not clear to me whether you made any use of the data that we provided you.
Yes, yes. As I mentioned in this slide, uh, if you go back, this one. So these are the points in the algorithm. These bits are the points, like the big integer is quite randomized. So they are, means these are the points where we have used the random numbers of the bits which
so
we
this
got
is
from
where
the.
you used our bits.
That's what I mentioned in the slide. These are the points in the algorithm. So there's a big algorithm, and when it is implemented in HLib library, it needs some randomization at different stages, maybe in the encryption, maybe in the noise generation.
Just to see, so I mean, these steps were taken using the random power bits.
Yes, yes.
Other questions?
I got a couple actually. Hello to everyone. I'm Luca, and
go ahead, Luca.
I have two questions. One of the slides you just show about how you use the random number generator, and it's not clear to me why you need the von Neumann extractor for the randomness. So did you?
No. I don't need a von Neumann extractor. It was just because at different stages here, if you see, in different stages in the algorithm. So these are the points. Like at 5 points, I've used the random numbers. So there different bits of random numbers are used. So it is not that 1024 bits random number are used at all 5 points. So I get a random number in chunk, and from that I extract whatever bits is required for different points in the homomorphic encryption using the von Neumann extractor. That's the role. Nothing required. If you can, you can also request at different stages of the algorithm from the QRNG, and you can use that as required number of bits. So because of the requirements, there are different bits. So I will.
Okay, thank you so much. And there is just another small point that you got quite right, and it was when you were talking about the side channel attacks, and you were saying that this essentially using this technology in the homomorphic encryption, you state that you reduce the probability of success of side channel attacks. But indeed, we have a physical device, and with a physical device, actually, you can, or maybe you can even enhance the probability of a success of a side channel attack because you have a physical device to attack and not just a RAM to read the noise or something like that. So can you comment a bit about this point, please?
Yes, I just told that we can reduce the probability, but side channel attacks will be there, always it will be there. But as I told in conjunction with some of the attacks like the RAM scraping attacks and some of the attacks which directly hits the memory and tries to gain some information from it, or because if you store in the memory the text or the information in a unencrypted and plain text form, then okay, or while processing in the RAM, if you are processing in an unencrypted form and there is a RAM scraping attack on that, that is a side channel attacks mostly, then there can be some leak in the information, which this homomorphic encryption can reduce because it is in the encrypted form and it's being processed. But I will tell there will be side channel attacks, but the probability is just reduced.
Okay.
So I'm just telling about the probability just because during processing, there are many attacks on RAM or the memory, so it will be reduced on that.
Okay, I see. And just the last one, then I leave the field to the others. And it's about the plot you showed. If we can get back to the plot, because they were not very clear to me. No, the previous one. Again, one back, please. No, maybe one more. Okay, this one. You see, there is a very huge jump between when you have 2 messages or 3 messages or 4 messages, and you have a jump of several several milliseconds. So it is just a fluctuation. Can you comment on this? Because all the other all the other plots, they have a quite regular pattern, and you can see that maybe there are just some fluctuation, but this seems a very big one.
Yes. So firstly, the x-axis are the message bits, so it's not the total message. So bits you can tell, and the y-axis, the difference is very less. As you can see, it's into 10 to the power -4. So the number variation is very less. I just zoomed in, so you are feeling it's quite means pointed out. But if you just zoom out and see the 0.0006 numbers and the variations, it's not much in that. So I just zoom in for showing purpose because the time taken is very less there in decimals.
Okay, so you did not run the test several times in order to get. Okay, I got it.
No, I didn't run the test.
Single snapshot.
A single snapshot. Okay.
It's a single snapshot.
That's clear. Yeah. So now it's clear.
So maybe whatever essentially.
Okay, thank you. Enough for me.
Thank you. Do we have any other question?
Yes, I have a question.
Please.
Can I? Sorry. So you say that you want to use this application for credit card payments. So as far as I know, homomorphic encryption has the possibility of making additions plain text plus ciphertext. So how do you plan to protect the system from someone just getting acquiring the control of a system? So a malicious attacker gets control of the system on the backend, and then he can add funds to his account, because he can, even if he doesn't know the encryption key, he could modify transactions in his favor. So how do you
are telling about
address
the
this?
addition or multiplication with a constant?
Yes.
Okay, so I think the constant is very much visible in the algorithm, if you can see, because that's why it's a constant. It's very much visible in the algorithm, and the main purpose of the encryption is if you make the algorithm public and it is known to everyone, and still people cannot use it to find a backdoor. So that's the main purpose of every cryptographic algorithm, and the constants are quite visible in the algorithm if you just implement it, because they are constants. So we are not using it to change it during the algorithm or during the information processing. So the lattice-based encryption doesn't rely on constants for its security. So it has other part of it securing the algorithm. So if you tell addition by constants or multiplication by constant, so okay, they have a part of information, but the encryption ensures that whatever information is there, which is not a constant, which is a ciphertext, that remains secure. So encryption applies on the plain text to convert into ciphertext, and the responsibility is to protect the converted ciphertext. Constant, it will be there. There will be some leakage of information, but okay, you can protect it with the ciphertext. That's the guarantee of lattice-based encryption. So,
thank you.
If you can, I just understand that. If you can tell anything, if you know something, because I know that's why I told.
Okay.
So
I can hear a voice.
Yeah. So my point was that I think I mean, as far as I know, there are no good solutions for that, but there should exist some kind of zero knowledge proofs and stuff to justify what is the processing that you're doing. And maybe you could potentially achieve that at some point. But in any case, if you just leave the homomorphically encrypted data, this data could be modified by any party and could potentially say that the payment was zero, both in transit or in transport. So it's really insecure in that sense.
Okay, you are telling modification of the ciphertext?
Yes, modification of the ciphertext in any
so
way.
I thought you were telling about the constant. So you are telling modification of ciphertext, and the receiver is not aware that it's been modified?
Yes.
Okay. Yes, that can be. And yes, as you told, something like zero knowledge proof, or you can have some things similar to QKD protocols, because QKD also worked on that. That if there is an interception.
Sorry, we are not time constrained, but we can really stretch it forever.
Sorry.
So it's very interesting. We will certainly continue. I know that we have at least 2 experts in the team, because I know that Jose is writing his PhD thesis, and also yesterday he interacted quite significantly with one of our speakers. So he's certainly somebody who knows a lot, and you as well. And I tell you, for instance, for random power, this is something very interesting. It's one of the applications that we are targeting. So thank you for what you did, and we will get back certainly to you, to both of you, to Jose and to you. Okay, thank you very much. If we have no other question by the board members, can I ask you? Okay, thank you. Now we move to team number 3, and it shall be Jan, if I'm not mistaken.
You're not
Give me
indeed.
2 seconds. I just open my bottle so at least I can drink something. Just hey, back in a few seconds. Eh?
I need them anyway. Ready when you are.
Okay, I'm back.
Okay, you should see me better now. So, thank you. First, thank you for joining us. I represent the True Random Privacy team at the hackathon. So, first, let me introduce us quickly. So, there is Jose coming from Spain. He's a doctoral student at CERN, and well, his main interests are cryptography, communication protocols, and as you saw, homomorphic encryption. Then there is Rustam. He comes from Russia, where he's senior research at Samara Aerospace University and Image Processing System Institute of the Russian Academy of Science. His main interests are image processing, pattern recognition, and data mining. And finally, there is me. I'll try to put myself in the frame, more or less. And so I come from Switzerland. I finished recently my PhD at CERN. And spent the last 2 years in Samara, same institution than Rustam, and my interests are noise data, IT security, and anomaly detection. So now the big question, what would we do with a pocket-sized random number generator? So during this hackathon, we decided to work on the topic of differential privacy specifically. So in short, differential privacy aims at sharing sensitive data publicly by applying noise on the data in a way that it withholds all information about the individuals in the data set. It's extremely useful, typically for medical images, topographical data, or basically any data set that shall not be shared, but which an external expertise is necessary for. So basically no more NDA taking weeks to sign or secret preservation issue. The benefit compared to, for example, anonymization is that anonymization is not generic, and that the guarantee, so the grant, depends on the data set. However, the differential privacy grant is done generically and is independent from the adversary capabilities. So in 2020, just as a reference, the US Census will release its data based on differential privacy instead of anonymization technique. Same with Facebook and recent COVID tracking data. So it's a hot topic at the moment. Of course, True Random was to be the heart of our product. Now that's a happy coincidence, so to say, because differential privacy has still no impediment, has still 2 impediments for its spreading. And the main one is that it relies on noise for its expression, and so far it relies on pseudo-random noise. The second is the difficulty to exploit privatized images. So according to that, we selected 3 tasks for the hackathon for our team. The first one, applying True Random generation to differential privacy algorithm. Second one, make sure that the privatized image usability, make sure of the privatized image usability by adapting a state-of-the-art key point detection approach on noise images. And the third one was to develop a use case with a demonstrated interest from the industry, useful for the random SPAO project future development. So useful for our organizers. So, true random differential privacy. Concretely, how do we apply true random privacy? First, what we do is we use strictly random numbers without seeding, and we transform them into a uniform distribution of floating numbers from 0 to 1. From there, we apply a Box-Muller transformation to change them to a Gaussian distribution and apply the Gaussian differential privacy mechanism. Then apply the noise on top of the image using dataset adaptive sensitivity calculation for noise distribution. This approach allows two things. Using first using a lower amount of noise to obtain the same privacy budget than pseudo-random, and an insurance that the noise applied cannot be reversed. Two things that existing approach do not offer yet, and that's a concrete problem. So you can see also there the equation.
We all have left and right problems, huh? And mirror symmetry.
It defines the probability of finding information about individuals in the data set. It's calculated according to the epsilon and lambda we set. So the lower the budget, the higher the privacy guarantee. So as stated in this formula, we proposed different privacy budgets dependent on image sizes, basically, so mainly at least. So in short, the lower the budget, the higher the safety. It's hard to compare with other approaches as it depends a lot on the application proposed. We selected, for the sake of challenge, a very low budget. As a comparison, it would be 15 times lower budget than Facebook proposes. So we are offering a lot more secure approach, and frankly speaking, almost obscenely secured compared to market stated requirements. But it's a hackathon, so we're here for the challenge, aren't we?
Sure.
So from there on, the next step was to find an application for that. And so we explained to you how true random addressed differential privacy's main concern. Now let's see how we propose to use these results. So one of the ways to use this image privatized using true random is feature descriptions. So we applied a feature description technique. Now the challenge was to get one robust enough to find features in privatized images. And the answer, well, came with the team, so to say. So creating a robust algorithm for key point detection was practically the title of my PhD dissertation. Okay. So Rustam, who is from our team, and I also worked a long time on feature description, and well, just like magic, we had a solution. So a sleepless night, kind of, and a year of coffee budget later, spent in this precise night, we came yesterday evening with an algorithm adapted to the problem. So you can see here on the top, right finger this time, some simple images and how the approach selects key points or area of interest on the image. It uses several shapes and then it uses different shape descriptors approaches to calculate key points, allowing to compare images. It was shown in several publications to be by far more robust than other existing technique. And yeah, so now the use case. So our two first objectives achieved, we had to do something with it. We really wanted for it to be usable. And the goal was to give the hackathon organizer really a strong use case, something you could use out of the box and take profit from other companies. So the use case we chose is key point detection on privatized image using differentially differentially privatized images. So to demonstrate the possibilities our project offers towards the medical industry specifically. So we are in COVID time, you know, it's kind of the seasonal trend. So
unfortunately.
So we took lungs images, still COVID related, but since we expect COVID, or we hope that COVID will stop someday, or at least won't last forever, we focus on something else. So here you can see 3 series of images. Those are PET scan, and they are successive, and our goal was to detect anomaly on those. In this case, the anomaly is a tumorous anomaly we wanted to detect this tumorous anomaly on the differentially private dataset. So here you can see on the top the original dataset. At this level, if my hands wants to appear at this level, you will see images after privatization, and on the bottom, feature descriptor traces run on privatized images. So just to underline one point, so it's clear and we don't get the question, the fact that we describe feature doesn't mean the images are not privatized. The fact we can retrieve the original content, we cannot retrieve the original content it is linked to shows that it is privatized. So this doesn't change anything to the privatization. And to conclude on this use case, so already on these images, according to the persistence of feature and their selection through the different descriptors, it's possible to detect anomalies, potential cancerous anomalies in this case. Not only that, but according to their development, the persistence, we could classify them. So you see here on the top, the seeked tumor that we are, the only one we wanted to spot, is the one that is labeled as level 2. So improving the detection anomaly process, it's definitely the next step. We are proud, honestly, to have gone so far in 2.5 days, but it's the logical next step. So what we have decided to do from there on is to hit the market a little bit, data privacy expert, medical institution, healthcare data specialists. And well, okay, with that I had underestimated something. We are in a hackathon, so sleeping and eating is kind of optional. Nobody thought about warning the other expert that we were consulting that sleeping is also optional for them. So we didn't have time to gather as many feedback as we would have liked. But we could have several. So we had one expert confirming the opinion and giving his opinion over the robustness of the noise, and I quote, "We can't see shit anymore." We took it as something positive. And also confirming an interest in using the approach. So based on true random to perform the similar task, we had a very, very good review from some medical research experts. So it shows that you might be able to use immediately this implementation of your true random generator to the medical industry, straight after this hackathon, so to say. So our hackathon results, so starting the presentation, I described you 3 tasks we aim at achieving. The first one was differential privacy generation application based on the true random noise you were giving us. It's a novel and so far unique implementation. Its implementation solved the 2 main hinders in differential privacy propagation. It can be used on any image to apply true random privacy, provided a bit stream. And we proposed you an adapted state-of-the-art descriptor for privatized images, allowing to perform complex comparison operation. And the third one is a use case of true random differentially privatized images with demonstrated interest from the industry. So we can happily say that during this hackathon, we achieved these 3 tasks. As you mentioned, as I remember, you mentioned during the introduction speech, you're looking for application of your generator in Horizon 2021-2022. So our goal was really to offer you such a product, and we believe that we could achieve that. And well, we deeply hope that that you believe the same. And,
okay, thank you.
It's split into true random differential privacy application, feature descriptor, and the use case. If there is an interest from your side, we will be very glad to guide you through it after the hackathon. So please just contact us if you have any question, and we hope you will find a direct interest in this project and it will be useful for the development of your companies. So that's it. Thank you.
Thank you.
Great time together.
Thank you. Very good, very nice. Congratulations to what you achieved, and congratulations to you and your teammates. I think you certainly did very well. It's and you advanced considerably, considering the two days and a half of coding, and the sleepless night and the liters of coffee that you had. Also, congratulations for the setup that you have for the optimizing the presentation. This is also very supportive to clarity. Okay, so for what concern feature extraction and anomaly detection, of course, anomaly detection is the name of the game, essentially. And in not only medical application, but in most of the applications. What, I tell you by my experience with the medical doctors, because as you can imagine, as a silicon detector guy, non-trivial part of what I'm doing is related to medical application. And also today we're running a big Horizon 2020 project on real-time dosimetry in radiotherapy. You really need to be good to convince medical doctor to use an automatized system. Yes. That's a matter of fact. And so they hardly trust a machine, and they hardly trust an algorithm. So what you have been doing certainly proves that you're doing well. Again, in order to have a full proof, you have to consider obviously a large image bank, and you have to compare the feature extraction on the privatized images with what you do with the unencrypted, also on the plain text, on the plain images. But this, I believe, you can achieve. The big problem in such applications, specific application, and not underestimating what you did, is certainly, to give you my experience, is that really medical doctors are human beings. They trust their own eyes, they trust their own experience. I tell you, this is something that I started realizing 20 years ago when I went to a medical imaging conference in Stockholm, where people were discussing, analysis of mammography images. Sweden is the country where you want to be if you're talking about mammography. There was one of the guru of mammography at the image conference and said, and discussion was about standard mammography and say PET-based mammography. That was very much pushed by the industry. Then this guru that was at the time even older than I am, so it was about 70, but he had an enormous experience, went on stage and he said, nobody can beat my eyes. And since then, most of the medical doctors I work with are actually telling me, fine, give me the instrument, give me the detector, but let me make a choice about telling you whether there is something funny or not. But okay, as I said, it's just to bring in some of my experience. What you did is really, really wonderful. It would be nice actually to see on a practical scale how much the use of our random power platform improve the security into the encrypted image. So I namely say, attack and decode and do whatever you like on an encrypted image according to a pseudo-random number and pseudo-noise. Do it with ours and tell me the difference.
Sounds like a hackathon topic almost.
Yes, it does. But you know, it's another way to say that we are certainly interested in what you did, for sure.
Thank you.
Other remarks or questions to Jan and his co-workers?
If there is anyone else that want to speak, I will give the priority to. I would like to have a couple of questions. Can I go?
Go, Luca, yes.
Great. So what you did is, of course, very interesting. And the thing that most catch me was the fact that you were able to extract features from the privatized image. This is quite impressive, I have to say. And I'm thinking in several applications, even in the industry, that goes well beyond the medical application. And specifically, I'm thinking about the image classification using deep learning or machine learning techniques for image classification. I'm thinking about faces, for example, if you have to recognize faces or things like that. As you mentioned, Facebook is one of the main market player that is using this kind of algorithm to identify faces, and this is raising a huge amount of question about privacy. Do you think that this kind of algorithm and this kind of application, the application that you just show us, can be used even in this field? There is something else that should be implemented, because I understood that you use a non-machine learning algorithm to have the feature extraction. So
I have written a dissertation about that.
Good.
I'll give the part of the answer. I think if we think about specific applications such as you mentioned, Facebook and Faces, I do not. I believe. I can say that the algorithm is efficient at recognizes that something is a face, but the goal of the algorithm is to select relatively large features, and that description makes difficult to separate, for example, different persons. This was really made and designed to work on noise data, and specifically it's used in the aerospace cluster. So for aerial captures, it's also made for piloting and 3D mapping systems, and it's also the reason of me being at CERN. So it is of significant use in the industry, but not much in typical very like precision operations such as Facebook face identification. Does it answer your question?
Yes, it does. Thank you so much.
Thank you.
Could I ask a question?
Of course you can.
So I'm not as good, obviously, and I haven't been deeply into the cryptographic world for too long. But one of my main questions is, it is like the work is amazing, but the problem is, again, to the image recognition thing. You can basically, there are enough PET scans through the years that you can take the reference of your picture and then are able in a way to extract the information that you need for the anomalies. So in a way, you can break it by just image research, right? Or in other ways, you can also break it by just looking at the way that images are distorted by the machines themselves, not by the algorithm. So is there a way to protect the images?
I think, yes, I'll have reinforcement in my team for giving a better answer than I could. Jose?
So as far as, differential privacy is meant for that, in the sense that it compares the sensitivity. The sensitivity is the variations that the different pictures have in the different pixels. So the idea is that with these pictures, you try to find which are the variations that are going through all the pixels, and depending on the variation that those pixels have in the different PET scans, you will apply more noise or less noise. So the idea is that if a pixel is carrying out so much information, the noise introduced to that pixel will be much higher. So regions, for example, that, as you said, carry information about the machine or some of these distortions, those informations should be noised much harder, and those practical informations would be hidden. So even if it's not perfect, so differential privacy is not perfect, so it's a probability definition. So it gives you a grant over how much information would be potentially leaked about yourself. So in our case, it's about 95% probability that no individual information would be leaked about yourself in the case that we just used. But it depends on the specific case. So it depends on expert hands to be using the data and to be handling it properly.
Okay, I understand. That's actually amazing. But again, from my simple understanding of cryptography, wouldn't someone that wants to break the algorithm feed the system different images with different noises and see how the algorithm obscures them, and in a way find out how to extract the images? Again, I do not know much. This is just a question.
So the idea is that the idea is that he cannot choose to put more noise or less noise. So the pictures are released with a certain threshold of noise, which is a certain protection, and you do what you can do with those pictures. If you need to reduce the noise, then it's not possible because you choose to release 95%. So 95% of the information free. You choose to remain that information hidden. So if that information is kept hidden, it's not possible to go back. So that's a property of differential privacy. So you cannot go back in principle.
So I need to have a little bit better understanding, because when we try to see the advantage of using quantum numbering in encryption, in image encryption, for instance, I studied a bit and I saw the standard way, by correcting where I'm wrong, that you start by having row scrambling. You usually start by having, say, column scrambling, then you have row scrambling, and then for every pixel, you have what is called diffusion. So you go from the original grayscale to a different grayscale. They can be mapping, or it can be adding noise. This is one of the options. Can you tell me, say, in a simple-minded approach, what is the principle of the differential privacy that you are applying?
Yes, so the idea is that differential privacy is not encryption. So we are not encrypting the data. We are just modifying it, just giving.
Yeah.
So
I mean,
it's the same as anonymization. In the same.
Yeah. What I told you is not exactly encryption. Is something similar.
Yes. So the idea is that what we are doing is making a modification on pictures, so that the probability of retrieving the original identity of an individual, it's a product
very
of
low.
Yeah, it's really low. So
so this is clear to me, but technically, as I told you, I mean, my standard way is that you do column scrambling, row scrambling, and grayscale diffusion. So,
yes.
So which are the basic steps that you take for your differential approach?
So first you have to define the functions that you're going to apply. So in our case, it's a small convolution that we perform. And then you have to define the variation of that function. Once you have the variation of that function, you can see how much sensitive each pixel is and each convolution is. So once you have that, you can choose what you want to do. And so you choose a mechanism, which is a specific implementation, or it's not an implementation, but it's a specific mathematical formula that allows you to to enhance the privacy of the picture, and thus reduce the information that it shares. So in our case, we chose the Gaussian mechanism, which is just adding noise based on a normal distribution, and the parameters of the normal distributions are based on the epsilon and delta that we showed on the formula, the probabilities, and the sensitivity.
It's essentially sort of diffusion. So sort of
kind of, yes.
So you have no row scrambling, no column scrambling, but pixel by pixel you make a sort of diffusion.
Yes.
So you change by convoluting with a kernel, with a Gaussian kernel, the grayscale of the pixel.
Yes.
Okay, and this is how you say, depending on the amount of information, I'm adding more and more noise, because this is something that was intriguing me, because you're saying If I have no information content, essentially, I don't care. If I do, then I just want to mask it properly.
Yes, that's it. So what you get there is that, so in fact, the way in which you add the noise is based on a Gaussian distribution, which in the end makes the probability of having the same value much higher. So in general, it depends on how secret it is that the standard deviation grows, and then the value goes farther away from the mean. So in general, the more private, the more standard deviation, the less likely it is that you will find the original value. So the idea is that the picture, if you, for example, talk about the same case that we had before with face recognition, in general, we treat it with face recognition, but in the end, we didn't find it interesting, or we couldn't apply our algorithm. But face recognition, what happens is you will see that there are certain areas such as the eyes or the ears, the color of the hair, that are really significant for the task. So if you apply differential privacy, the sensitivity is going to find that these areas are more interesting, so it will include some noise in that areas, and you will see that the hair of the people may change some color in a slight way, so that you can understand that there's a blonde person, but you cannot understand which tone of blonde it is, so that it doesn't identify the specific person, but a range of people who are blonde in the end.
Okay, so my final question, because I like what you're saying, but just to make sure I got it right. So say you're doing what we call as physicists Gaussian smoothing. Okay, it's a different way. But
yes, kind of.
Kind of. But then again, for instance, the most probable value, the Gaussian that you use, is centered on the grayscale that you have. I just talk about grayscale to make it simple. So because you're smoothing around the peak value that you're starting from.
Yes.
Right? Okay. Then the other question is, you're doing something where you're changing, for instance, the sigma or the Gaussian that you use, which is to me saying I'm moving sharply where I am, or I move away from where I am, throwing my dice. But then I have to see how relevant, as you said, the information content is. For doing so, then you have to not to be local, but you have also to look around you. So you make an analysis at the boundaries.
I'm not sure I'm understanding correctly.
We do it. It's becoming a bit complicated. We do it later.
Yeah,
we do it offline.
That would help you.
Yes.
That would be more clear. Jose, you remember the face that you sent me?
Yes.
With really the description of the informativeness of each pixel.
Okay, gentlemen, it's definitely intriguing. We move on and then we continue the discussion offline.
Okay, thank you.
Okay.
Thank you and good luck.
Thank you.
Okay, we have 2 teams to go. So next one is going to be team 4. And if I'm not mistaken, it's going to be Valeria.
Hello, can you see me?
Not yet.
Okay, just a minute. I try to share the screen. Can you see the presentation?
Now you can, yes.
Okay. So I would like to present a protocol that is called together with a piece of hardware that is able to secure the transmission of TCP packets along any kind of network, or to securely transport random bits generated by random power to different kind of clients that cannot be physically linked through a USB cable to the random power hardware. So the problem we would like to face is how can we apply the the true random generator security of random power to different kind of application, for example, to VPN tunneling or generation of keys for Wi-Fi clients or mobile devices. So we tried to design an hardware device that is called the quantum tunnel endpoint. The quantum tunnel is the name of this protocol because I worked to make it enough sure to face attack that can be possible in future thanks to quantum computing. And this endpoint need to be linked only in one point of the communication, while the client receive a stream of true random bits in an encrypted way through the network, and so it's not necessary to have a couple, and the client can be a mobile device. And in this way, it's possible to create very secure point-to-point communication or client-to-site communications. So let's see a bit the overall topology of the system. We have this quantum tunnel endpoint device that is made of an electronic board with two SFP slots that can host a fiber optic transceiver or an gigabit Ethernet port. The bandwidth of the two ports is 10 gigabit per second, and this device hosts inside the random power electronics. So you can link this, you can connect this device to a server or a desktop PC or a network on an inbound, a local network port, and the public network port is connected to the internet or to a public connection. So what happened is that there is a secure exchange of keys using an external packet relay server between the client and the quantum tunnel endpoint device that make it possible this protocol to work without opening any kind of port and without removing any kind of firewall or changing the network configuration. And this allows to secure communication on different kind of protocol in different network topologies. So what happens is that you can specify a query inside using a particular interface that I will present soon. And you can specify a query that is applied on TCP packets that when a TCP packet satisfies this query, all the entire packet or a portion is encrypted while is passing through the device. And the portion that satisfied the query is encrypted using an AES 256 bits algorithm that is supported by the key generation and the initialization vector generation by the random power to random generation device. What happens in that when this TCP packet with inside the encrypted portion of data come to a generic client, the client can't display the content, but it is possible, for example, to specify an alternative text, an alternative content that is shown. But when this packet come to a client that has installed the quantum tunnel client, this quantum tunnel client, thanks to the external packet relay server, can contact the endpoint that encrypted the content, and there is a secure exchange of keys and of initialization vector that allow to make a secure connection using AES 256 and the true random generated bits for the keys. And in this way, the pair of keys is transferred from the hardware endpoint to the client. So the software ecosystem that make possible all these things is made of a firmware running on this piece of hardware, a client that in the current implementation that is only a proof of concept is running in Python, but can be written for all kind of mobile platform. The packet relay is use Python scripts on an Apache web server. And the control panels are the editor of rules, that is the software that I've written using C# on Visual Studio, but can be written, for example, in C++ to be multi-platform compatible. And in this software, I can I can use a packet sniffing technology to see all the packets that are passing through the interface of the endpoint. Then I can choose to create a query that can filter a certain type of packet, and this packet will be encrypted during the path through the from the endpoint to the client. And this interface is able to create this kind of rules. There is also an embedded firewall that can block these kind of packets, and this is important for some application that I will present. For example, a first application could be securing an existing remote desktop connection of a company, for example, using RDP protocol that today is considered unsafe on public networks, but without changing any type of network configuration. Is it possible? And it's not secure because now it's exposed to active man-in-the-middle attack. It is possible because I can create a new rule on the outbound port of the endpoint hardware when I specify that all the RDP packet must undergo encryption, and so all the packets are inspected, and if satisfy the query, the RDP content is encrypted, but it's totally transparent to the protocol, because when the packet reaches the client, before forwarding the packet to the operative system, apply the decryption. Another interesting application is, for example, for website administration. I can have a website. For example, this is the website of my university. I can, for example, specify a query that intercepts a particular HTML tag. And when the client has not installed the client, the Quantum Tunnel Protocol client, the alternative text can be normal plain HTML or JavaScript content is shown. But when I access to this resource using a computer that has installed the client, I can see a content because I can decrypt a portion of the packet that reached my PC. And this is possible only by creating on the server endpoint. So this is only on the server side. So it is very simple for the clients. They only need to have the private certificate to have access. I can create a rule that intercepts this particular HTML tag. After, if it is time, I would like to show some code that do exactly that. Another important use is that we can use this protocol to transfer random bits in a secure way. And it is possible because there are some magic words, some tokens that if they are found on a packet that is traveling through the endpoint create a response that does not contain the normal response to the packet, but instead create a response that is a direct access to the true random bit generator. So in this way, by only creating requests with this kind of tokens inside, I can use the endpoint as an hardware, as a container for the random power quantum to random bit generator. So a very quick overview on how this protocol works. All the RSA and elliptic curve encryption protocols now is known that can be forced using quantum computing technique, in particular the Shor's algorithm that implements a quantum Fourier transform can reduce the computation time needed to force this kind of asynchronous encryption algorithm significantly. And so the only way is to use AES 256 that can be forced the Groover's algorithm, but only by dividing by 2 the numbers of k to be tried in a brute force attack. But AES is not completely secure because there are known many issues that create catastrophic effects when initialization vector and keys was not completely unpredictable. And this is the way in which the random power generator came inside the game and can resolve this problem. So it is some few lines from a particular AES implementation I created that use the bits from the random power through quantum through random number generator to create the initialization vector and the keys, also ensuring the authentication. There is a third party that is the relay server, but it is only to prevent the opening of port to allow the direct communication from the client and the endpoint. But all the traffic is completely public, and so there are no security issues if it is attacked. And so it can be, for example, deployed on Google Cloud Platform, Amazon Web Services, and so on. It is just hosts some tables that are used to prevent some endpoints to have the same unique endpoint IDs and unique certificate IDs. So very briefly, when you exchange a packet that satisfies the query, the content is replaced by this scheme. And so you can you have a random quantum tunnel protocol identifier, then a unique session ID and an hash of the endpoint ID, and then the encrypted content. It is sent to the client. At this point, the server opens a connection through the packet relay server and just wait. The client receives these packets, and if the client, so the piece of software client of the quantum tunnel protocols is installed, intercept this packet, contact the relay server, and the relay server, thanks to the hash of the endpoint ID, can redirect the packet exactly to the endpoint piece of hardware, but without contacting him directly. That requires an open port on the endpoint, but just by replying to the open request that the endpoint sent to the packet relay server. At this point, is established a secure channel communication between the endpoint hardware and the client software through the packet relay server that allow the exchange only of the initialization vector and of the keys that are new at every packet exchange. So every key is used only once by Bob, by the endpoint, and once by the client, while the initialization vectors are all used only once while both Bob and Alice, so the client and the server. And this is basically the scheme of this communication protocol. Okay, so that is, okay. Another interesting point is that using a normal distributed interval of times, the communication protocol randomly distributed in this way can ask to the client to update the private key certificate. What happens is that the endpoint creates a new couple of keys and initialization vector that is sent to the client, and that is written directly replacing the current copy of the private key certificate. In this way, if you try to attack the key used in one communication, you are gaining only the key for one packet, because if the time you need to force the key is higher than the time the system needs to exchange two packets, the key you are calculating is completely unuseful. While what happens on the certificates is that if you can grab the key of the certificates, you can virtually open a new connection. And in this way, also this scenario is avoided by periodically synchronizing a new certificate that is created using true random number bits by the endpoint. This is the structure in bits of the certificate. It contains a cache of initialization vectors ready to use, because in the first step of the connection from the client to the server, the client has not yet access to the true random bit generated by the endpoint. So let's see a proof of concept at work. Now I try to share some Python code if I have enough time. Okay. Can you see the Python notebook?
Yes, yes, we can, Valerio.
Okay. Yes, it's only a proof of concept, very, very quick. But so in this code, you can see, for example, This is the point when you download in real time from the server of the hackathon the bits, and you create a stream that can feed the requests of the endpoint. This is the implementation of the EAS that is partially, I've partially used a GPL licensed code, so open source, usable for this kind of things, but in partial I have to modify some section to optimize it to this specific application. It is an OCB AES encryption, and in this way it's possible also to have integrity check and authentication in every packet exchange. At this point, you have the code, the capture, this is the configuration of interfaces. You have the real-time capture of packets. You have the inspection of packets with delimiters that in this simple case specify the query, but can be, for example, a regular expression that is more powerful. In these steps, you have the definition of the certificate that in this first proof of concept is a dictionary, but it would be written, for example, in C++ because it's quicker to run on embedded systems, but now it's a certificate. And then you have the functions that at high level use the AES functions to encode the blocks that are traveling through the IP network channel. So in this step, okay, in this first step, you have the capture of the traffic. Then you have the endpoint outbound interception and encryption. So the packet is intercepted and replaced the text with the encrypted one. And then you have the client that receive the encrypted packets. And so using the hash of the endpoint ID can contact the packet relay server. At this point, you have the key negotiation protocol that starts using the third-party server between the client and the endpoint server. Okay, and then you have, for example, the update of the certificate that in this case is implemented in an extremely simple way because it's only a